Tomorrow morning, you open the curtains and discover that someone has installed Saturn's rings around Earth. No warning, no permission, and absolutely no instruction manual. Shipping Saturn's rings would be unreasonable. Since those iconic loops are 90% water ice, bringing them to our warmer neighborhood would simply melt them away. Instead, a terrestrial ring system requires Earth to manufacture its own from rock and dust. This happens when a passing asteroid or a stray moon wanders too close, crossing an invisible boundary called the Roche limit. First calculated by Edouard Roche in 1848, this is the cosmic point of no return where a planet's differential gravity, the unequal gravitational pull on the near and far sides of an incoming object, overcomes its cohesion. The tidal forces literally pull the invader apart. We know exactly how this looks. In 1992, comet Shoemaker-Levy 9 crossed Jupiter's Roche limit, fracturing into 21 distinct pieces before colliding with the giant 2 years later. Some scientists suspect a similar event happened here 466 million years ago during the Ordovician period, leaving a brief ring of debris that peppered our equator with meteorite impacts. But this does not form a solid spinning track. In 1859, James Clerk Maxwell mathematically proved that a solid ring would tear itself to pieces under gravitational stress. Decades later, in 1895, James Edward Keeler used spectroscopy to confirm that planetary rings are actually billions of independent particles, each orbiting like a tiny satellite. Because Earth is warm, these particles would be composed of dark silicate rock and dust rather than bright ice. This glittering, particulate river would align itself perfectly with the equator, setting up a striking display of orbital geometry. Because this particulate stream is locked into Earth's equatorial plane, running perpendicular to our axis of rotation, your daily view of this cosmic highway depends entirely on your latitude. If you stand directly on the equator, the entire system collapses into a razor-thin, luminous line slicing straight through the zenith, dividing the sky perfectly in half from east to west. Travel north or south to 30 degrees latitude, near cities like Cairo or New Orleans, and the geometry opens up. Here, the thin line expands into a spectacular sweeping arch that dominates the heavens, reaching a maximum elevation of 60 degrees. As you journey further towards 60 degrees latitude, near places like Helsinki or Anchorage, the arch sinks much closer to the ground, hovering just 30 degrees above the horizon like a permanent, glowing bridge. Finally, near the poles, the ring remains a low, horizon-level feature, barely peaking above the frozen horizon. These dramatic differences are purely a matter of perspective relative to one fixed plane. The ring itself never actually changes shape. And because it is anchored directly to the equatorial bulge, it does not rise and set like the moon. Instead, as Earth rotates, the ring remains pinned to the sky, an unmoving guidepost in the celestial sphere. Instead of a dark sky, those billions of rocky particles scatter sunlight back to Earth, bathing the night in a perpetual, lunar-like wash. Yet this glow is never uniform. While the sun-facing side of the arch gleams brightly, Earth's massive shadow, or umbra, cuts a dark, moving gap straight through the ring rather than hiding it completely. For ground-based observatories, this extra sky glow raises darkness ratings on the Bortle scale, making faint galaxies and distant stars nearly impossible to isolate. Astronomers would develop a new professional hobby. Complaining, to survive, they would have to pivot toward infrared wavelengths, adjust their schedules, or rely on space telescopes. Below the sky glow, ecosystems face potential disruption. It is possible that migrating birds, spawning corals, and nocturnal predators would struggle with the altered light cycles, though the exact biological toll remains uncertain. This nocturnal glow also shifts as Earth moves around the sun, dragging massive shadows across entire continents. Earth spins on an axis tilted at approximately 23.4 degrees. Because the ring system remains fixed to the equator, this planetary lean creates a shifting relationship with the sun. Over the course of our year-long orbit, the angle of incoming sunlight changes, dragging a massive, moving shadow across different latitudes. Instead of a permanent dark zone, dense bands of rock and dust cast traveling shadows that migrate north and south between the tropics. Earth would gain another settings menu, as if weather needed one. Huge ground-based solar farms would experience significant seasonal drops in power generation as the ring material passes directly between them and the sun. It is also possible that these migrating shadows could alter regional temperatures and wind patterns, though the exact atmospheric changes depend heavily on the ring's thickness and composition. But while humanity on the ground watches these shadows sweep across continents, an even more immediate engineering headache unfolds higher up, in the crowded lanes of orbital space. This orbital barrier does not mean every satellite is instantly vaporized. Instead, it reshapes where and how we fly. Spacecraft operating safely below the ring, or positioned far above it in high Earth orbits, can bypass the hazard entirely. The true danger is concentrated where orbital routes physically slice through the densest bands of debris. Polar satellites are particularly vulnerable. They must plunge through this celestial highway twice per orbit, turning every single lap of Earth into a recurring roll of the dice. After all, a rock does not need to be angry when it is moving several kilometers per second. To survive, launch planners must map out temporary gaps and low-density corridors within the shifting rocky stream. Rockets can punch through the ring plane rapidly to minimize exposure, but long-term satellites will require constant trajectory adjustments. Tracking networks would have to monitor millions of individual drifting stones, updating collision paths in real time. Ultimately, getting to space remains possible, but the path becomes a complex, highly coordinated puzzle, and a much more expensive one. Inside this celestial ring, a relentless grinding machine is at work. Constant collisions smash larger boulders into fine dust. While massive fragments remain trackable, drifting as individual hazards, smaller particles face a different fate. Sunlight and pointing Robertson drag slowly sap the energy of the finest dust, while the thin upper atmosphere drags down lower altitude debris. Like the material Cassini observed raining into Saturn at thousands of kilograms per second, Earth's ring would slowly bleed inward, vaporizing as silent meteors. Over time, orbital spreading and gravitational clustering would carve gaps and assemble transient moonlets. Much like the projected decay of Mars's moon Phobos, this entire system is a temporary feature. It is a spectacular orbital clock, slowly winding down with every single revolution. A sky dominated by a giant arch would fundamentally change human society. At 30 degrees latitude, cities like Cairo and New Orleans would become hubs for ring-viewing tourism, their economies buoyed by travelers seeking the perfect view of the celestial span. Annual festivals would track the predictable march of the ring's shadow, turning solar events and recurring meteor displays into global holidays. Artists would weave the sweeping arch into city skylines, paintings, and national flags. Traditional navigators would use the fixed geometry of the ring to chart courses across oceans, replacing ancient star maps with a permanent overhead grid. In classrooms, children would draw a ringed Earth as naturally as they draw trees, while their parents still remember the terrifying shock of the day the rings arrived. Yet, this beauty brings friction. Communities would fight to preserve what little darkness remains, debating new laws to shield observatories from the relentless ring glow. And while families gather under the glowing arch, space agencies and insurers would face a grim ledger of soaring satellite coverage costs. The ring would become our ultimate clock, its gradual shifts documented across generations as it slowly grinds away. Today, we take our empty night sky for granted, but imagining a ringed world reminds us that Earth's greatest luxury is its quiet, open dark. Perhaps the true spectacle isn't what we could add to our heavens, but the fragile beauty we already have. Share your thoughts below.